Hello, this is my Chapter 4 review for Calc. I figured I would do myself a big favor for at the end of the year when we have our exams to review each chapter. So, starting with Chapter 4. So, first section in the chapter was about extreme values. And you'll be given a function and an interval. And it'll ask you to find the min and the max of the given function on the given interval. So the first thing I like to do is take each number on your interval and plug them in as x values in your points. So like that, and then you're going to plug both of those numbers into your original function. These are our points for our interval, and now we're going to want to take the derivative of our function. So that's our derivative, and now we're going to want to set our derivative equal to 0, and we want to see what makes this equal 0. We want to find our critical points. So then 16 to the 4th power is just plus or minus 2. So 2 and negative 2 are our critical points. So we want to plug both of those into our original function, not our derivative function, our original function, to see what our y values are, and then compare them with the original points from our interval. So for this one, I get negative 128, and then for negative 2, I get positive 128. So we just want to see what's the lowest y value between these 4 points, and that's this one right here. So this is going to be our max value. And then we also want to compare these 4 points to see what is our highest y value, which is this one right here. So this would be our, or wait, sorry, I got that mixed up. This would be our min. Sorry, it's like midnight right now and I cannot think. This would be our max because this is our largest y value, and this would be our min because it's our smallest y value. So that pretty much sums up 4.1. So for the steps, you just want to plug these numbers in, get these 2 points, then you're just going to take your derivative, set that equal to 0, and see what numbers you get from that, and just compare it with the original answers. Pretty easy stuff if you ask me. Okay, moving on to 4.2. 4.2 talks about the mean value theorem. Okay, so for mean value theorem, you're going to be given a function and an interval, just like in 4.1, but instead of finding the min and the max, it's going to ask you to find a value c that satisfies the mean value theorem for the given function on a given interval. So the first step you're going to want to do is, just like up here, you're going to want to set both of these into points and find your y value by plugging it into the original function. So this first one's just going to give you negative 1, and the second one's going to give you 2. So then you want to plug these points into this function to get your slope. So this is what it looks like once you plug these points into this function, and you're going to get 3 over 1, or just 3 as your slope. So this equals m. And then you're going to want to take your slope and set it equal to the derivative of your original equation. So to do that, we have to take our derivative first. So our derivative would look like that, and then we just want to plug this in for this, and just solve this for x. And I get x equals a half. So this is your value of c. I guess I should write that as c equals 1/2, but it means the same thing. So that is our answer when it asks for c. If it asks you for the point, you just have to plug 1/2 into your original function to get that point. And I get 1/4. So yeah, pretty easy. You just have to remember, to take the derivative and then set that slope equal to your equation. So yeah, that sums up 4.2. Now on to 4.3. 4.3 talks about points of inflection. So just like up in 4.1, you're going to want to find your derivative, but then you're going to want to take it a second time to get your acceleration function, which is going to give you your inflection points when you set that equal to 0. So you'll start out with a function that they give you, and then they'll ask you to find the max, min, and inflection points of these functions, and sometimes they'll also ask you when is this increasing and decreasing, and when is this concave up and concave down. So first thing we want to do is take our derivative. So that's our derivative, and we're going to want to take it again to get our second derivative. So that's our second derivative, and then we'll deal with our first derivative first, so we can just get that over with, find our critical points. So to do that, we're just going to set this equal to 0 and find what makes this 0. And I get that x equals 0 and x equals 1 makes this 0. So these are our critical points. And we want to plug both of these values into our original equation to get our critical points. So I get this is 4 and this is 5. So this is going to be our local minimum, and this is going to be our local max, because this point has our highest y value. So this would be our max, and this would be our min. And then if it asks you where it's increasing or decreasing, so this should look like this interval, and if you plug in a number less than 0, you get a negative number, which means it's decreasing. If you plug in a number between 0 and 1, like a half, you get a positive number, so you know it's increasing. And if you plug in a number larger than 1, you get a negative number, so that tells you it's decreasing. And so for concave up or down, I figured I'd go into more depth about it. So this is what your critical points and inflection points look like. These are your inflection points, the ones that have the open circle, because that's where it switches from concave down to concave up, and then these are your critical points, which is your mins and maxes. And usually you can tell without having to do a bunch of equations what your graph is going to look like based on your exponent. So if your exponent is even and your leading term is positive, your graph is going to look like this with your endpoints, with both ending going up. And then if you have an even exponent but a negative leading term, it's going to look like this, where both points are going down. And then if you have an odd exponent, your graph's going to look like this, with it going up to the right and down to the left. And then if you have a negative leading term with a odd exponent, it's just going to flip around. So that's how you can tell without really doing any math, if you just memorize that stuff. So, yeah. For the velocity function, you want to do the same thing, where you set this equal to 0. And solve for x, which I got x is equal to 2. And when you're checking if this is concave up or down, you look at the acceleration function. And you want to put this into your interval. And you want to pick a number that's below 2. And you want to pick a number that's higher than 2 and plug that into your acceleration function. And so if you plug in, let's just say 0, because that's less than 2, you get 6, which is a positive number. so that means you're concave up. And then if you plug in a number that's bigger than 2, so let's just say 3, you get a negative number. So that means you're concave down here. So that's how you do 4.3. That's how all that works. Okay, on to 4.4. Okay, 4.4 talks about optimization. Optimization is kind of scary, but it's not that bad, and there's some common problems that you'll see a lot, and those are like the fence perimeter type problems, and there's a lot of them that talk about open topped boxes. So first question is, a box with a square base and an open top must have a volume of 32,000 centimeters cubed. Find the dimensions of the box that minimizes the amount of material used. So first you want to draw your little picture. So fun. This is my little picture. And then it mentions that there's a square base. So you know that these have to both be x, and then this is your y. And then you want to write your volume equation because it tells you in the problem that the volume has to be 32,000 centimeters cubed. So that's going to be your volume equation, since x times y gives you your volume. And then it wants to know what dimensions of the box minimize the amount of material. So that's asking for surface area. And the surface area for this cube would be this equation, because x squared gives you this bottom part, and this is open top, so that's not 2 times x squared, it's just once, plus 4xy, because there's 4 sides where you're multiplying x times y to get the area. So I hope that makes sense. So now we have to find a way to get this in terms of y so we can plug it into this equation. So if we set y equal to 32,000 over x squared, which that's just rearranging this, and then we can put it into our surface area equation for y. So it should look like that. And now we just want to simplify. So that's what this looks like after we simplified it, because 4x over 1 times 32,000 over x squared is just 128,000x over x squared, and then the x on the top cancels, so we're just left with this. And now we want to take our derivative of this simplified equation. So to do that, to make it easier for us, we're going to want to flip this x up on top and make it 128,000 x to the negative 1. So that's what I get once we do all that math, and we can simplify that even farther to look like that. And then after we get that, we want to set our derivative equal to 0. Okay, my camera died. It was overheating, so I finished the work here. So you solve for x, and then you get x cubed equals 64,000. So if you take the cubed root of 64,000, you get x equals 40. So then to get your y value, you want to plug that x into this top equation that you used when you got y by itself up here, and plug 40 in for that. And then when you do that, you get y equals 20. So those are your ideal dimensions of this problem. These also, for optimization, these are the most common problems that we're going to see. I kind of wrote them with dumb names, but there's word problems where it'll ask something like find two integers where the sum of the first and 4 times of the second number is 1,000 and the product's as big as possible. Those aren't as common, but you know, we were asked that a couple times when we were learning it. This is a really common one with the shoreline fence where you have like one side open. The open top boxes are really common as well. The scary looking parabola things that actually aren't that scary. Minimizing distance, that's a common one. And then the L-shaped triangle cult leader ones where you have to use your Pythagorean theorem. Then you also have ones with the cutout squares, that one's a pretty common one too, and then the sectioned off fences. Those are all the main ones that we practice. I'm not going to do an example for each one because we would be here for literally hours, but that's your general overview. Okay, so in 4.5 we talked about linearization, and usually you're given a problem like this where it says use a linear approximation to estimate some type of function. And I should note, linearization is kind of stupid because we have calculators to figure this out, so it's kind of pointless, but it's on the exam, so that's why, you know, we have to learn it, I guess. So even though it's pointless, this is how you do it. So with linear approximation, you're always given a number that's really close to a number that's easy to divide or multiply or whatever it is. So for this problem, it's 3.98 to the 4th power. 3.98 is really close to 4, so that's going to be our a value. So our a value is just going to be whatever nice number is close to our x value, which 3.98 is our x value. And then we also want to identify f of a and f prime of a. And our f of a we get by plugging 4 into this equation and just multiplying it to the 4th power. And we get 256 for that one. And f prime of a is when we take this and instead of writing 3.98, we just put an x in and we take our derivative. So it's going to look like that. And then our derivative of that is just 4x to the 3rd. And then we're going to plug in 4 for x and solve. And I get 256. You're not always going to have the same number there. That's just how this one worked out. And we want to use all of these values to plug into this equation right here. So you're going to want to do L of x, so that our x would be 3.98, equals f of a, which is 256, plus your answer from plugging your x into the derivative, which is also 256, and then do x minus a, which would be 3.98 minus 4. So that would be our equation, and then we can solve that, and when we solve it, we get L of 3.98 equals 250.88 is what I got, which also matches my answer key. So that's how you do linear approximation. I'm not going to do another example, but if you have an example with a square root, like square root of 65, you would just use 64, and it's the same process as up here, but just with a square root. So don't let those scare you, because that's silly. Okay, we're on to our last section, thank goodness. 4.6. So 4.6, we talked about related rates, and related rates occur when you have two variables changing at the same time in a problem, and we have to get our equation in terms of one of those things to figure out the problem. So the most common types of related rates problems that will likely show up on the exam are the problems that involve conical tanks. There was a lot of questions about that, and it's a very common one to see show up. So we're going to do an example of those ones. So the problem says water drains from a conical tank with R equals 8 meters and a height of 10 meters. If the water is draining at a rate of 15 meters cubed per hour, how fast is the height of the water decreasing when h equals 7, or height is 7? So first we want to draw our little picture, the best part. That's our little tank. And then we have a radius of 8 meters. So that's 8. And then we have a height of 10 meters. And the question's asking, what rate is the height of the water decreasing when the height is 7? So it's asking us to find dH dt. And so we're going to want to plug 7 into our equation at some point. And if you look at our little tank here, our radius and our height makes a triangle. So what does that mean? Pythagorean theorem. I'm just kidding. No, it doesn't. It means geometry. So this is your R and this is your H. And this is our original triangle. So this proportion is always going to be the same. It's always going to be 8/10, but just smaller or larger depending on how much water is in your tank. So you know these two are related. So if we do 8/10 equals R over H, and we cross multiply, we get 8H equals 10R. And then we want to get that in terms of R. So we can do 10 divided by 8H to get 4/5 H equals R. I should also mention that the volume of our little tank here is this equation, 1/3 pi r squared h. Since the original problem states that the water is draining at a rate of 15 meters cubed per hour, that tells us our dV dt is 15. You should probably do that in the beginning, but it doesn't really matter until you have to start plugging numbers in. So after that, we want to plug in the numbers that we can before we have to take our derivative. And since we know R equals 4/5 H, we can do 4/5 H squared and simplify this equation. So 4/5 squared is 16/25, and then H squared times H is just H cubed. And then 1/3 times 16/25 is 16/75. So you're left with that. And then once we get this is as simplified as we can get. So now we want to take our derivative, which looks like that. And then we can multiply 3 times this to simplify. And we get 16/25 pi h squared, I forgot squared up here, dh dt. And now we can plug in all of our numbers that we have from up here into this equation. So we know that dv dt is 15, and we know h is going to be 7, and we don't know our dh dt. So now we can solve for dh dt. We get dh dt equals 0.1523, and that's in meters per hour. And that matches with my answer key, so we did it right. So that is probably the most common question, or the most likely, that we'll see on an exam. Hopefully this video helped. If anyone else is watching, hello, this is kind of awkward. Good luck on your exam!